Good afternoon, everyone. My name is 𝙍𝙤𝙗𝙤𝙾𝙪𝙥 and I'm pleased to present the Sim2Real AI Robotics Challenge. I've had the privilege of working on this project with my teammates Sarah, Darren, and Jawad. Together, we aim to push the boundaries of robotics by bridging the gap between simulation and real-world robotics. Goal of the challenge. The goal of this challenge is ambitious yet crucial: to bridge the gap between simulated environments and real-world operations. By leveraging RCAP CoSpace Vision, NVIDIA Jetson, and ROS, we work to develop robots capable of executing efficient search and rescue missions in both virtual and physical settings. This Sim2Real workflow forms the foundation of our project, and we believe is a significant step toward creating adaptable and intelligent robots for challenging environments. CoSpace Vision Simulation. Computer vision and RGB sensors form the foundation of our simulated robot's capabilities. Find objects. Using computer vision, the robot detects collectible objects by analyzing their size and color. Color tags. The robot detects wall-mounted color tags to identify specific zones and make precise navigation decisions. April tag navigation. By identifying and decoding unique April tags, the robot performs predefined actions such as navigating or depositing objects. RGB sensors. These sensors are used to detect objects and avoid traps during navigation. Combining RGB sensors and computer vision. By integrating April tag detection with RGB sensor data, the robot effectively identifies and avoids traps. Some capabilities we developed was using laser scans. The robot was able to generate maps to navigate its environment efficiently. Now, let's take a quick look at a demonstration of the CoSpace Vision simulation in action. This short video highlights the robot's ability to detect objects, navigate using April tags, and avoid traps, showcasing its versatility in the virtual environment. With our current robot simulation, this project aims to bring it to life using the NVIDIA Jetson with share. Now let's draw some parallels between our robot and Google Waymo, a leader in autonomous driving and a subsidiary of Alphabet. Waymo focuses on developing safe and efficient, fully autonomous driving systems, and there are a number of similarities between their technology and ours. First, both systems use obstacle detection. Waymo's LiDAR detects objects by measuring distances with laser pulses, just like our robot does, enabling it to adjust movement to avoid collisions. In terms of environmental scanning and mapping, both systems use a laser-based navigation scanning system to create a map of their surroundings. This allows for more accurate navigation. When it comes to visual recognition, Waymo uses cameras and machine learning to recognize traffic signals, pedestrians, and objects. Similarly, our robot identifies red, cyan, and black tags on the ground to detect its environment. Lastly, both systems rely on real-time decision-making, using image processing to quickly classify environments and ensure fast responses. This is crucial for real-world applications where quick and accurate decisions are needed to ensure safety and effectiveness. Project Overview. ROS, Robot Operating System. We use ROS as a middleware framework, enabling smooth integration between hardware and software. ROS allows efficient communication between components and simplifies development with its modular, flexible functionality. AI and Machine Learning. Machine learning creates a virtual safety bubble, allowing for safer navigation. The robot is trained with images to adapt and move effectively in various environments. AI powers autonomous decision-making, navigation, and object recognition. For our hardware, we have LiDAR sensors, camera, GPU, and CPU. Sim2Real. Simulation. Navigation and obstacle avoidance were trained in a virtual environment using computer vision and RGB sensors. Real-world adaptation. The physical JetBot uses advanced sensors to enhance functionality. It uses LiDAR for 2D mapping and real-time obstacle detection, ensuring precise navigation. Camera is used for April tag localization and enhanced visual-based collision avoidance. This improved performance as, by adapting our simulation strategies to the physical robot, we achieved greater accuracy, reliability, and efficiency in real-world navigation. NVIDIA integration. We utilized NVIDIA technology to take advantage of its advanced hardware and AI capabilities, boosting the overall performance of our system. Collision avoidance, machine learning. We feed images captured by the JetBot's camera into a pre-trained model, ResNet-18. By using this pre-trained model, we significantly reduce computational time and save resources, as it eliminates the need to train a new model from scratch. This approach leverages the power of an already optimized model, enabling efficient and effective collision avoidance. We replicated the simulated map by designing a physical map with additional obstacles for the purpose of model training. We did a total of 5 steps for the machine learning process for collision avoidance. To begin, we split the dataset into 2 labels for the classification task, blocked and free. Blocked. These are images that show the objects that the robot must avoid. Free. These images represent clear paths where the robot can move without obstruction. We start by capturing images of clear maps with no nearby obstacles, allowing the robot to recognize paths where it can navigate freely. Next, we also include scenarios where obstacles are further away, so the robot can continue moving until the obstacles come closer and require avoidance. For better training, we take close-up pictures of obstacles in various sizes, colors, and shapes. This ensures the model learns to detect a wide range of obstacles. The dataset should also include varied settings, such as dim lighting, different object orientations, and varying distances to account for real-world variability. This makes the dataset more robust and helps the model perform well in diverse environments. An ideal dataset should look like this. Step 2. Model training. Next, we input the collected images into ResNet-18, a pre-trained convolutional neural network model designed specifically for image analysis and computer vision tasks. The advantage of using ResNet-18 is that it automatically learns and extracts features from the images, reducing the need for manual feature engineering. The 18 in ResNet-18 refer to the number of layers in the model's input and hidden layers, allowing it to efficiently process and understand complex visual patterns. For our training, we specified a total of 30 epochs. This number was chosen based on the need to generalize well, ensuring the model performs well across a variety of unseen data, reduce overfitting. By limiting the number of epochs, we prevent the model from memorizing the training data and failing to generalize to images, and minimizing computational cost. Training with 30 epochs strikes a balance between effective learning and reducing heavy computational load. Step 3. Model optimization. To optimize the model for faster performance, we convert and optimize it using Torch2TRT, a tool that leverages TensorRT for accelerated inference. Before feeding the camera images into the model, we pre-process them to match the neural network's input format, ensuring smooth data flow. TensorRT, developed by NVIDIA, is designed to optimize AI models for real-time performance. It fine-tunes the model's layers to process data faster and more efficiently, which is crucial for applications like collision avoidance on the JetBot. By utilizing TensorRT, we enable quick data processing, allowing the JetBot to navigate more efficiently and safely by making faster decisions. Step 4. Running collision avoidance. In this step, we deploy the trained neural network on the JetBot while it navigates the physical map. The model processes camera images in real time to detect obstacles and avoid collisions, allowing the robot to move safely through its environment. By integrating the optimized model with the JetBot's hardware, we ensure seamless operation and effective collision avoidance, even in dynamic and unpredictable conditions. Step 5. Fine-tuning. If the model does not perform as expected, fine-tuning is performed by repeating steps 1 to 4 as needed. This step is crucial for improving the model's accuracy and performance. Fine-tuning is often the most time-consuming phase, as it involves multiple rounds of testing, data collection, and retraining to achieve the desired results. In our case, it was essential to train the model to reliably avoid boundaries when near them, move away from untrained objects, and operate effectively in various environments, including carpeted surfaces and differently colored grounds. An example of a poorly trained model would be one that frequently collides with objects or fails to navigate smoothly in different lighting and terrain conditions. These videos show how we have trained our model to perform and handle different terrains while encountering new obstacles. Next, we have April tag detection. The robot uses April tags with predefined IDs to represent important elements like deposits and traps. These tags are taken from the virtual map. The JetBot utilizes its camera to perform pose estimation, determining both its position and orientation in the space based on these tags. It calculates coordinates and rotational angles relative to the camera. Through ROS, the system is configured to detect, seek, and track specific April tags. These April tags serve as markers to guide the robot, instructing it to perform certain actions based on its location and task requirements. The JetBot architecture. The APROTAC detection can be understood as consisting of three main layers. The hardware layer. This includes the physical components that make up the JetBot, such as motors, encoders, and IMU, Inertial Measurement Unit. These components provide the essential functionality and sensory capabilities for the robot's operation. Secondly, driver layer. The driver layer consists of software that directly interfaces with the hardware components, enabling communication and control over the various sensors and actuators. This layer ensures the hardware operates smoothly and correctly. Thirdly, the service layer. The service layer includes Jupyter Lab Server for web-based control, allowing for easy interaction and management of the robot. ROS Publisher Notes for tasks such as camera calibration, APROTAC navigation, and SLAM, simultaneous localization and mapping, which are crucial for autonomous navigation. It also handles communication through the ROS Master, which runs on the JetBot, managing the interaction between all system components. Challenges as ROS beginners. As beginners in ROS, we encountered several challenges, especially in understanding the coding process. Specifically, we struggled with how nodes publish and subscribe to topics, and how to control the JetBot through these nodes and topics. This graph was incredibly helpful in clarifying how nodes and topics interact. It showed us how nodes subscribe to and publish data to each other. This visual representation made it easier to understand the flow of information and how commands are passed through the system. One key realization was that we needed to use this interaction to publish commands to the node, so the JetBot could recognize when to stop and execute other actions. In this video, you can see that the JetBot is programmed to approach the APROTAC until it is close enough, then stop for 3 seconds, simulating the virtual robot's deposit behavior. LiDAR. LiDAR, short for light detection and ranging, plays a crucial role in environmental sensing and navigation. In vehicles like Google Waymo, LiDAR is particularly valuable in navigating ever-changing environments, where lighting conditions can vary. Its ability to operate effectively in darkness makes it an ideal technology for ensuring safe and precise navigation in any setting. Looking at LiDAR, this is how it works. Using a 360-degree environmental scanning, it enables comprehensive spatial understanding by scanning the entire area. To measure the distance, it utilizes pulsed laser light and measures the time for the reflection to calculate distances. However, the JetBot's A1 LiDAR has its limitations of detecting objects of only up to 12 meters away, which is sufficient in providing detailed mapping in our case. To have a visualization of the map generation is done using SLAM, simultaneous localization and mapping. It is a technique used to build a map of an environment while simultaneously keeping track of the robot's location within it. SLAM uses the robot's sensors to detect the environment and make real-time updates to both the map and the robot's position. LiDAR overview. For our use of LiDAR, we do live mapping, which is a live representation of our surroundings. SLAM, which generates a detailed and accurate digital map for navigation, object following so that the robot can follow moving objects, such as a guide or rescuer, and object avoidance to continuously scan the surroundings to avoid objects. This is how live LiDAR mapping is done. Firstly, data collection. The LiDAR captures both distance and angle data from its surroundings, and invalid readings are filtered out to ensure the data remains clean and reliable. Secondly, polar plot. This data is visualized in a polar coordinate system where angle represents the direction and distance indicates how far objects are from the sensor. Thirdly, color coding. To enhance clarity, points within the sensor's range are displayed in one color such as blue, and points outside the range are shown in a different color like orange. Visualization. The resulting plot provides a real-time view of the environment, helping to identify nearby objects and obstacles. These visualizations can also be saved as images for further analysis and record keeping. There are 3 types of SLAM algorithms, but we decided to use Gmapping for our robot due to its efficiency and compatibility. The Gmap is generated by a SLAM and shown using RViz, which is then saved for future use. It's good as it's lightweight and efficient, making it ideal for low-power devices like the JetBot. It's perfect for creating accurate 2D maps in small to medium-sized environments, and it's well-tested and widely supported within the ROS ecosystem, ensuring stability and reliability. However, it relies heavily on accurate odometry, which can be a challenge in environments with uneven surfaces or wheel slip. It's less suitable for large or highly dynamic environments where 3D or advanced SLAM methods may perform better. Had three algorithms, 𝙑𝙯𝙗𝙗𝙑𝙗, and greedy best first search, and chose 𝙍𝙗𝙗 for its effectiveness. It guarantees the shortest path, and it is easy to integrate with G-mapping. Even further, I will explain how 𝙍𝙗 algorithm works and is implemented in the autonomous navigation of the JetBot. Firstly, a map is created with lidar, where the map is divided into grids as shown in the image. Each grid is a point, also known as a node, and the connection between the nodes have weights based on distances or cost. To carry out the multiple point navigation, the JetBot starts at the first set point, which is 0, and calculates the shortest path to reach the next target, which is 1, as indicated in the image. After reaching the target point, it recalculates the path to 2, which is the next target, ensuring it efficiently navigates all provided points in order. While ensuring that the JetBot travels the shortest distance from point to point, the lidar updates the map, marking obstacles with high weights. 𝙍𝙗's algorithm naturally avoids these areas by favoring paths with lower overall costs. In the videos here you can see how the JetBot moves on the map, and its pathway can be seen on the G-map that was created and saved in advance. The points 0, 1, and 2 are set in advance, and the JetBot relies on 𝙍𝙗's algorithm to move. In search and rescue scenarios, the robot assists by following the rescuer, carrying essential tools, medical supplies, and communication devices. This reduces the rescuer's load and prevents slowdowns, allowing them to focus on the task at hand. So firstly, the robot continuously scans its surroundings using lidar to detect the closest object. Objects within the priority zone are given higher importance for more precise tracking. When an object is within the tracking range, the robot calculates the required speed and direction and uses proportional derivative (PD) control to adjust its movements accordingly. If the object moves out of range or gets too close, the robot stops to avoid potential collisions. This system ensures the robot can consistently follow a moving object while avoiding obstacles, making it an ideal tool for autonomous navigation, assistance, and surveillance. Demonstration of the object following being carried out in real life. lidar collision avoidance. The robot continuously scans its environment using lidar, dividing the area into left, middle, and right zones. When an obstacle is detected, the system flags the corresponding zone based on a configurable safe distance threshold. How it works. The robot moves forward if no obstacles are detected. If the front is blocked but the left side is clear, it turns left. If the right side is clear, it turns right instead. If both sides are blocked, the robot chooses a direction randomly. It constantly adapts by adjusting speed, sensitivity, and turning behavior to ensure smooth and safe navigation, even in dynamic environments. Here is a demonstration. Development process, we encountered several challenges that tested our abilities: hardware issues, time constraints, environment challenges, and a steep learning curve, as well as software issues. Looking ahead, the next steps for the project are as follows. We want to combine all functionalities: collision avoidance using machine learning, collision avoidance using lidar, and apotext detection into a unified system. This will ensure the robot operates seamlessly and can adapt to real-time changes in the environment. Look ahead, the impact of autonomous technology continues to grow across various industries, from self-driving cars like Google Waymo and Tesla's Autopilot, which rely on lidar and computer vision, to warehouse automation where robots use Sim2Real concepts for picking, sorting, and inventory management. Robotics is transforming efficiency and precision. In search and rescue, AI-driven robots equipped with sensor fusion can navigate disaster zones, helping to save lives in critical situations. Meanwhile, drone technology is advancing rapidly, with applications in delivery, inspection, and aerial mapping, all benefiting from Sim2Real training for real-world accuracy. As these technologies evolve, they will play an even greater role in shaping the future of automation, making tasks safer, faster, and more intelligent than ever before. Finally, we would like to express our deepest gratitude to the following individuals and institutions: Dr. Zhou, Mr. Hans, Dr. Yang, Madam Shen, and Singapore Polytechnic. Their unwavering support, resources, and guidance have been instrumental in the success of this project, which has helped us push the boundaries of robotics and achieve our goals.